work, so I guess. Okay, it works. Very quiet this morning.
I was so stressed. I was like heading here. My computer decided to restart. Then Zoom was kicking me out because I was logged in as Steph. It was like all over the place. I had to ship something and like before coming here. And it didn't work because this printer thing didn't want to, print out the label. It was all, yeah, a stressful morning, all in all.
Well, we all made it. Hello, everyone. So, Anna, it's your
Yes.
turn.
Hello, good morning, everybody. Thanks for joining. We are again co-hosting. Are you excited, Steph and me? Name a better duo. Um, all right. So today, 1 hour earlier, not really, but like for our systems, 1 hour earlier, Müge is going to present a paper that is not a nature paper. That is gonna, that's an exciting change for Neuroccino. So Miga shared the link already in the chat. Steph, if you want to copy it to YouTube. Hi, Hervé. Awesome, that is done. Hello, YouTube audience. And without any further ado, Muga, take it away.
Oh, thank you. Okay, so let me share my screen. Okay. Okay. Are you seeing the right screen?
Yes, we are, I
Okay.
think.
So, do I need to make it larger? But
That works.
that works?
Perfect.
Okay, cool. Yeah, so today I picked this paper from Sivan Yosinger and et al. So it's about the contribution of cerebellar peduncles and frontal aslant tract in mediating speech fluency. Because this is really closely related to my work about speech fluency, and I don't see a lot of papers about cerebellar peduncles. So that's why it was of great interest to me. It's a neurobiology of language paper published last summer. So this is so fluent speech production is a complex task because it involves both language, linguistic aspects, and also some motor aspects. When we produce speech, it requires conceptual framing, so we need to, plan what we're going to say, and then it requires lexical access, so we need to pick the right words to say what we want to say, and it also requires phonological encoding, meaning that we need to pick the right sounds to articulate those words, and eventually we need articulatory, like motor control, to make the right muscle movements, motor movements to produce those sounds. And so humans do this like very efficiently. Humans produce about like 16,000 words every day. Didn't know that's probably it's more for some of us and less for others. But yeah, on average, like 16,000 words and 150 words per minute. So, so how do we produce this, fast speech so efficiently? A lot of papers, when they try to understand the neural substrates of fluent speech production, they use different tasks to measure fluency. And some of these tasks are verbal fluency tasks. For example, they would give you minutes to produce words that start with a certain letter. For example, this is phonemic fluency task. And then in other papers, they use, for example, semantic fluency tasks. They give you 1 minute to produce words that belong to a certain category, like produce words that are like vehicles or like animals. So these phonemic and semantic fluency tasks are widely used, but these are actually measuring linguistic aspects of speech, so linguistic fluency, right? Because in these type of tasks, you need to do lexical access to find the right word from your like mental dictionary. And in other type of tasks are related to more like motor aspects of speech. So, speaking rate, articulation rate, so that kind of fluency. So in this paper, they use all these tasks. So for the speaking rate, is this speech rate fluency tasks, they measure speaking rate. So this is like this measures the number of syllables produced per second. But they also have this articulation rate. So this is the number of syllables produced per second. But when you exclude all the disfluent speech segments, for example, when people stutter, or they repeat something, or they pause, they exclude those kind of disfluencies, and they call it the articulation rate. So if you include all these kind of disfluencies and then measure everything over the whole speech segment, they would call this the speaking rate. So in any case, in this paper, they say that these different tasks measure different aspects of speech. So the verbal fluency, like phonetic or semantic verbal fluency task, they measure lexical access. But the other, the other tasks measure speech rate and articulation rate, like syllables per second. So one measures the lexical, the linguistic aspects of fluency, and the other measures the motor aspects of fluency. And in the literature, these are usually, measured separately. They either focus on the verbal fluency, or they focus on articulatory control. And they usually, a lot of these studies are done with disordered populations, like in populations with stuttering, with aphasia. So in this paper, they decided to target neurotypical population, and then they want to do both kind of tasks, both verbal fluency tasks and articulatory control tasks. And now one question that they're asking is cerebellum so important for the linguistic or motor aspects of fluent speech production? Because a lot of times cerebellum is thought to be like motor structure that's that plays an important role in the motor control of speech. So they are looking into whether cerebellum is also important for other, linguistic aspects of fluent speech production. So yeah, they give examples from like previous studies of patients with cerebellar lesions, show impaired verbal fluency abilities. And neuroimaging data show that a lot of times during verbal fluency tasks, cerebellum is activated. So they want to see if this is like actually the cerebellum is important for this verbal fluency task, or it's just showing an effect of articulatory, like motor activation. So they focus onto cerebellar peduncles. So cerebellar input and output information is carried by three major white matter pathways known as cerebellar peduncles. So there is inferior, middle, and superior cerebellar peduncles. So basically, this inferior cerebellar peduncles carries signals, like peripheral signals, from spinal cord into the cerebellum. And these middle cerebellar peduncles and superior cerebellar peduncles are thought of as pathways within the cerebrocerebellar loop. So these pathways carry information between the cortex and the cerebellum. So the middle cerebellar peduncles is an input pathway into the cerebellum. So the cortical signals come to the cerebellum, contralateral cerebellum through pons. So this is the middle cerebellar peduncles are involved in this. And there's the superior cerebellar peduncles, and this is thought to be the output pathway from the cerebellum to the cortex. This pathway carries signals from cerebellum to the cortex through thalamus. So in this study, they look into these three different tracts, and also they look into the frontal aslant tract, which is another important tract that was shown to be involved in speech production, and then this tract connects supplementary motor area with the inferior frontal gyrus, so IFG and SMA connection. And then they also focus on this tract because this tract is shown to be affected in people who stutter, and then people with multiple sclerosis and chronic aphasia. So this is an important tract in speech production, the motor control of speech as well. Okay, so they evaluate cerebellar peduncles and frontal aslant tract in neurotypical adults. And then they have like 45 participants in this study, which is quite a big number. And they measure verbal fluency and speaking articulation rates, speaking and articulation rates through different tasks, and they do diffusion MRI in these participants. So basically, they extract different white matter metrics, these different microstructural metrics, and then they correlate them with different measures of speech fluency. So, okay. So in this, speech fluency assessment, so they, as I mentioned, they have these speaking rate and articulation rates. So in these tasks, they ask the participants to do some, unstructured interviews. They ask them to talk about a topic, like about a recent travel, about a recent book that they read or a movie, and then participants talk about this, spontaneously, freely for about 10 minutes. And then they measure syllables per second. And for speaking rate, they measure the whole thing. But for articulation rate, they exclude disfluent speech segments and then measure the syllables per second. And for the verbal fluency tasks, they give participants 1 minute, and then they to produce words that begin with a specific letter in Hebrew, like bet, gimel, shin. And then in the semantic fluency task, they ask participants to produce words that belong to either animal category, fruit category, or like vehicles. And okay, so they do. Okay, so here they do both tensor modeling and then constraint spherical deconvolution. They use the results from the tensor modeling to calculate these metrics like fractional anisotropy FA and I mean diffusivity MD. But they use the spherical deconvolution results to generate the tractograms. So generated tractograms. Okay, so in this figure we see these different tracts. So we see the cerebellar peduncle tracts, and then on the right we see the frontal aslant tract, and they also calculate the individual tract profiles at different notes. So this figure, the C and D, show how FA, fractional anisotropy, changes through the throughout the tract. So yeah, they use these like 30 equidistant notes. And so yeah, this is each line here is one participant, basically shows the tract from one participant. And okay, okay, so yeah, so here in the results, we first see the behavioral correlations. So a lot of these different measures like verbal fluency and like articulation fluency, they might be correlated. So they first look into these correlations. So of course, like speaking rate is correlated with articulation rate. And in this case, like this, for example, semantic fluency is correlated with phonetic fluency. So because these some metrics are have these intrinsic correlations, they use a partial correlation analysis. So if they find a significant correlation, they follow it up with a partial correlation analysis to account for the these kind of intrinsic correlations. And so it's important here. And then they look at the correlation of these different white matter metrics with the task, the verbal fluency or articulation rate correlations. So here we see for example, right medial cerebral peduncle, and then throughout the whole tract. So if they look at the track FA or track MD, they can't find a correlation with any of the fluency measures, speech fluency measures. But then when they do these distinct nodes analysis, they found the cluster here. And then the metrics from this cluster, so the FA from this cluster or the MD from this cluster, they correlate those cluster metric with the speech fluency metric, and then they find a correlation in the right medial cerebellar peduncle with the speaking rate. And they do it for the superior, the other metrics, and they also for the superior cerebellar peduncle, they find a correlation of FA in this cluster with the phonemic fluency. And for the inferior cerebellar peduncle, they didn't find a significant correlation with any of the speech metrics. And for the fat, so they find also for the bilateral fat, they find a correlation with speaking rate. So basically, this is the fast like snapshot of the results. For the right medial cerebellar peduncle and the right superior cerebellar peduncle, they find white matter associations with speaking rate and phonemic fluency. And for the bilateral fat, they find again correlation with the speaking rate. Okay, so for the discussion, so this basically shows that they also look at, for each subject, they look like how speaking rate and articulation rate is correlated. So of course, articulation rate is always larger than the speaking rate because it includes disfluencies. And then, so for disfluencies, how they calculate disfluencies for each participant, they look into that, and then they look into the amount of like different disfluence segments. So interjections, revisions, repetitions, phrase repetitions, stuttered syllables. So all these kind of things caused disfluencies. So basically they look into the behavioral aspects a bit more closer here. But okay, so if we summarize, what they find here in this paper, so they show that speech fluency measures map onto different white matter tracts. So some measures like speaking rate are associated with some white matter tracts. Other speech measures like verbal fluency measures phonetic fluency is associated with a different white matter tract. And then they show that like cerebellum, so they show that none of the tracts are associated with articulatory rate. So articulatory rate, if I remind, they exclude disfluent speech segments and then calculate the syllables per second. So that means that it doesn't include any like pauses or hesitations or repetitions. So it's basically like how fast your muscles produce a word. So they claim that articulation rate does not include an language, linguistic aspects, because you don't pause there, you don't hesitate there, so it doesn't measure your lexical access, so it's just very motor. And then none of these white matter tracts measures are associated with articulation rate. And then they say that that's why we can say that cerebellum is not only a motor control structure, because none of the cerebellar peduncles metrics are associated with articulation rate, and it's rather involved in linguistic. So it's rather, it's involved in linguistic rather than purely motor aspects of speech. And then they also say that another clue is that right cerebellar tracts are involved in these, are associated with these kind of different speech measures. So right cerebellar lateralization we see in this results. So right cerebellar lateralization in linguistic operations makes sense, considering the left cortical lateralization of the language. Uh, so and then yeah, because the connection between cerebellum and the cortex is crossed. So that also is another clue showing that cerebellum is actually doing some kind of like linguistic processes. And then they also show that fat frontal aslant tract contributes to higher level linguistic operations rather than pure control, because it's also not correlated with articulation rates. It's correlated with speaking rates, but not articulation rates. So all these tracks that they tested are doing more than purely motor control, are involved in more than purely motor control. They are involved in more, linguistic aspects. So I think, how am I doing in time? Yeah, so it's just to wrap it up. I thought that this paper was interesting because they try to segregate these different kinds of aspects that makes our speech that are involved in fluency, these lexical and motor aspects. But just I had a couple things that was not super clear to me, some concerns. So the tasks used in this study depend on different cognitive factors beyond language, and then I'm not fully convinced that these are factored out here. For example, in the unstructured interviews, they asked participants to tell, they give them 10 minutes to spontaneously talk about their, one of their vacations, but this requires a lot of access to memory. So this has a lot of memory aspects. So it's not completely ruled out here. And in the other, the other question I had was, like these cerebellar peduncle associations with fluency, they don't find these kind of associations when they look at the white matter metrics throughout the whole tract, but they only find these associations when they look into like certain clusters of this throughout the tract. And then they usually find these clusters near the decussation points. So they say that,
Miguel,
yeah,
no, I don't want to interrupt you, but we have 5 minutes left for discussion, and the
yeah.
discussion is starting to be very heated in the chat,
Oh,
with
really?
especially Eduardo
Okay, let's
gonna
get into
totally
it.
take on the lead here, and has a lot of questions. So Steph is even
Okay.
stepping
So yeah,
back.
that was my last point anyways. So these were my,
Awesome.
yes.
Sorry for the interruption. Thank you very much for presenting your paper. And
Yep. Thank you.
Eduardo, there you go. The stage is yours.
It's okay. Just throwing me under the bus like this. Okay. Fair enough. Yeah, Miguel, thanks for presenting the paper.
Mhm,
So one of the last point you raised was actually one of my questions. And I was like a little bit weird to me that they found these correlations at the crossing point.
mhm,
So I was wondering whether they mentioned something about like these, but and also another point related to these correlations with the like behavior tract correlation is that there seems to be like quite a dishomogeneous distribution of the correlations like within the tract itself, like for all the tracks
mhm,
pretty much so, but also it's particularly striking for the fat.
mhm,
But you have like areas of positive correlation, negative correlation, and zero correlation. So I was like,
mhm.
um, yeah, I
Yeah.
struggle to understand a little bit the meaning of like all these
Yeah.
and whether it's reliable or whether there's like maybe some technical issue with this.
Yeah. So this first, this high correlation for the decussation points. I don't know. So they say that FA, this FA measure tends to go down during around decussations. Is this a common thing? I don't know. Like, is this a common observation? Yeah. So okay. So the yeah, they say that we look at different tracks, and this strong FA correlation is only we see for the superior cerebellar peduncle, but not for the medial cerebellar peduncle. So if this was a spurious correlation, we would see this for all the tracks around the decussation points. So we don't see it for all the
Mm.
tracks. We see this correlation only for this certain track. So that's why it cannot be spurious. That's what they're saying. But yeah, it's if you look at the images here, that's very
But what was the resolution of the data they had, for example? Uh,
uh,
because I mean, the peduncles are relatively big, but also I guess like not so big and not so easy to dissect.
mm, yeah, I don't know the answer to that from the top of my head, but yeah. Mm. Yeah, so this is where
Um,
they show the correlations throughout the track, and then yeah, it's always around those nodes around the decussation. They see these like increases, decreases. So I'm not sure about that. And if the what was the other question? Sorry, Eduardo.
Yeah, the other question was about this oscillation between positive and negative correlations, especially in the fat. But
Yeah,
basically, yeah, they seems to like have like these core areas of positive, like I think it's last figure 6 or something.
yeah.
Yeah,
Um,
because I
Yeah, so
mean,
they, okay. Oh, here I remember. So they don't look at the correlation with the nodes here when they report the results. So they say that bilateral FAT is associated with speaking rate. So this is here, they find this association when they take the metric from the entire tract. So they also, to be consistent, they also did the node analysis, but here the results are not from the correlation of the node with the speech fluency. So because yeah, for the different nodes, they find like different patterns of correlations.
Okay.
But yeah, here what they report here is the tract FA, so not node of cluster FA, but tract FA.
So just the overall fractional
Yeah.
subgrouping.
And I was also, so they do both tensor analysis and then the spherical deconvolution. But why do they still use FA and MD? That part is also not
Oh,
clear.
okay. I didn't know that. I thought they did like probabilistic on spherical deconvolution data.
Yeah.
Okay. Yeah.
They have a
We're
b-value
gonna
of 1000. That's why the DTI probably, or the tensor model probably comes in.
Mm,
Oh, okay.
okay.
since our time is we are already over time, but
Okay. Lilith has a
yeah, that's
question.
why we're gonna move on and take Lilith's question.
Okay.
Yeah. Hi, Muga. Thank you again for presenting this. I have a question about the multiple correct, because it seems like there are a lot of tests on behavioral level within tracts, across different measures. So, and they are saying that they did it just within tract correction. Why don't they do like across tract and across measures? Because it seemed that it can increase probability of positive significance results just by chance.
Within tract connections, I think they do, and they do the node analysis. So when they, look at the correlation of the node FA with the speech fluency, and they do it for 30 different nodes, they do correction.
Yeah, but they have
tract,
a hypothesis in general, right? That is there a correlation of these tract metrics with this type of behavior? So if there is no cross behavioral measure correlation and between MD-FA also testings with the different measures of behavior, then they might get just random significant levels where it's not actually significant. I don't know.
No, I think they do that too. They do. So for the nodes, they do the family-wise error, but for like for these between across correlations, they also do FDR, I think.
Yeah, because I
They
think
do.
on the page, wait, there is a page somewhere, like 685, a long tract correlation. It says that family-wise error correction was applied across the 30 nodes within each tract, with no further correction across tracts, behavioral measures, or diffusion metrics. So I was trying to understand the reason why they didn't do like, because it's a lot of statistical tests. So I don't know. And also family-wise error is not that conservative, so I guess you could also do like the whole, I mean, in comparison to Bonferroni, I don't know. So yeah, it's just the question about this, because yeah, a lot of comparison, and might be this just happen so to appear significant. Yeah, that was my question.
Yeah. Yeah, I'm not quite sure. Yeah, it's
yeah, I guess it's just better.
Yeah.
I need to read the paper and see the reasoning why. Also, maybe like
there
they
was
explain in those papers that they cite. I don't know.
Would have been interesting if they didn't only correlate basically the tracts with the function, but also looked into like bigger networks, for example, to kind of double check. So yeah, that is for a
like
follow-up of
unrelevant
this.
tracts, right?
For
as a
example,
control. Yeah.
for example. All
Yeah.
right. If there are no further questions, I'm sorry, I'm gonna skip the questions from Steph in the chat because we have already ran out of time. Then thank you again very much, Miga, for presenting.
Thank you.
Very,
Yeah.
very elaborate and very, very cool. Yeah, presentation. I enjoyed it a lot. Thanks a lot. And yeah, I wish you an exciting week in science. Happy Monday. And yeah, thank you all for joining. See you next week.